Okay, so we're going to learn some definitions of words relating to graphs, and in D1, this that you can see in the top right, that's a graph. So not a graph like you know, a graph like that. This is what we mean by a graph. Okay. So first one, a path. Right. Now, do you want to write it as I say it, because that will help get it into your brain a bit. So a path, it's a finite sequence of edges. Okay. And the end of one vertex, no, not the end of one vertex, that's nonsense. A finite sequence of edges, right? The end vertex of one edge, the end vertex, that's the end like corner, blob bit on the end, of one edge, is the start vertex of the next in the sequence. So essentially, they're joined up. The edges are joined up, right?
So, finite sequence of edges,
Yep.
the end vertex
Yep.
of one edge
Yep.
is the start vertex of another.
Good.
Right.
Now there's one other important thing about a path, which is that no vertex appears more than once.
So no
vertex. So no, you can't go back through a corner.
Okay.
Okay, and then that's a path. Okay, so do you want to maybe change the colour and see if you can draw a path on that graph? Any path you like. That is perfect. That is a path. Yeah. What's the longest path that you can do on that graph? I mean, not you don't have to really think about it, but just do a nice long.
Okay. So.
Yeah.
Am I allowed to go to E?
Well, you are allowed to go to E. What you get then is a closed path, which we're coming to next.
So I shouldn't do that.
Well, at the moment, what we're looking for is a finite sequence of edges, which is what you've got. You've got 1, 2, 4 edges.
Yeah.
The end vertex of one edge is the start vertex of the next. You haven't jumped anywhere, and you've got no vertex appearing more than once. So I think just stop there. That is the path.
Okay.
Yeah. So it doesn't have to go all the way around. It could just go from E to A,
Okay.
and then from A to B. That would be a path as well.
Cool.
Okay. Right. Now a cycle is a closed path.
Right.
Now, they do ask definition questions in D1, and you do have to get the definitions right, and it's worth quite a lot. What's difficult is when a definition includes a word which is itself a definition. So in an exam, what is a cycle? It's a closed path, that's fine. But closed itself needs a description, and path is what we just did.
Mm-hmm.
So in an exam, I tend to look how many marks it's worth and maybe put brackets. A path is a finite sequence of edges such that blah, blah, blah. Okay? So a cycle is a closed path. So what the closed bit means is that the end vertex of the last edge is the start vertex of the first edge. Yeah? So it still has to be a path.
Yeah.
It still has to be a path. But the end vertex at the last edge is the start vertex of the first edge. So do you want to stick a path on there? Not a path, a closed path. Yeah, perfect. Closed path. Yeah,
Okay.
brilliant. Okay, connected. Now connected refers to two vertices. So maybe like B and D, or B and E, or B and A, or B and C, or something like that. So two vertices are connected if there is a path between them.
Okay.
So if you can put a path between two vertices, then they are connected.
So E.
They're connected, yeah. In fact, I mean, is there a pair on that graph that aren't connected?
Right.
No. So every vertex in that graph is connected to every other vertex, so that's called a connected graph.
So if I had a line coming out of that,
Yeah.
is it not connected?
What's that going to? An edge would have to go to a vertex. So if you put a vertex on the end of that,
Yeah.
yep, and that would be vertex F, that is still a connected graph because you can get from F to every other vertex via a path.
Right.
If we did this, G, H, I, whatever, this is part of the same graph, that is no longer a connected graph. This is not a connected graph because you can't get from G to A, B, C, D, E, F via a path. There is no path from G to F because you have to jump. Yeah? So that is not a connected graph. Whereas if we get rid of this bit and have a look at the original, that is a connected graph because all the vertices are connected.
Okay.
Okay. Tree. Now, a tree is a connected graph.
Right.
Yeah. And within the graph, there has to be no cycles. Did we do cycle?
Yes.
Yes, we did cycle, didn't we? So, do you remember what a cycle is?
That is where you can. That's where you can just go between the vertexes, isn't it?
A cycle was a connected. A cycle was a closed path.
Right.
So path is edge, all joined up. If you close that, if you come back to the beginning, that's a closed path, which is a cycle. So what we're looking for is a connected graph, which we've got because all of the nodes are connected, because there's a path in between them all, but we can't have any cycles.
Right.
Now at the moment, you can see on this graph, there are loads of cycles.
Yeah.
The cycles all over the place. You could start at E, go E, A, B, back to E, that's a cycle. You could go E, C, B, E, that's a cycle. So what we need is to take out some of the edges to make a tree.
Right.
Because at the moment, this is not a tree. It's got way too many edges on it. Okay, so what you're going to draw is a tree. Now what you're going to draw here is a connected graph with no cycles. Right. Have you created a node in the middle? I don't think you're really allowed to do that.
Right.
There isn't a node in the middle.
Okay. So
a connected graph
without cycles.
without cycles.
Hmm.
So connected means every node is connected to every other node via a path. Yeah, that's one.
Right. I
Yeah.
see.
So you've got every node, you can get from A to everywhere else, and from everywhere to everywhere else on a path, but there is no way using those edges you can create a cycle. You can't start somewhere, move around and get back to where you started
Yeah.
on a path. And don't forget, on a path, no vertex appears more than once. So when you're moving around, you only visit each node once on the path.
Okay.
Okay, so that's a tree. Now actually, what you drew there was also a spanning tree, because a spanning tree is a tree, if I want to put the definition on, it's a tree which includes all the original vertices. Now, sometimes this models up students, because if you look back at our other one, they say, well, hang on a minute, we had to do everything, because, you know, we included everything on this one. Now, if we take out this edge, right, what we've got here is a tree.
Yeah.
This is a connected graph with no cycles. Now, it doesn't include A.
Yeah.
So if we just put our sort of pen around this is a tree, and this tree is a subgraph of the original graph.
Mm-hmm.
It's not a spanning tree because it doesn't include A, but it is a tree.
Okay.
Okay? If we had G over here, we did that, and then we did this is not a tree. Because trees are connected graphs, and as taken as a whole, this is not a connected graph, because I can't get from A to E, B, D, C. Not by a path, because I'd have to jump. So this entire thing, that is not a tree, because it's not connected. Because the AG bit is not connected to the E, B, D, C bit.
Via this pathway.
Via any pathway. Via any pathway. If you're stood here at G, there is no path to B.
No.
So that graph is not a tree.
But what's the difference between forget G?
Yeah. And A.
This
No, A still
just
there.
A
Okay.
itself.
Yeah.
On here, it's not connected.
No.
But it is connected on here.
Yeah. So it depends whether or not you are asking the question: is this a tree, or whether you're saying is this a tree.
You said you can't invent another node. This has invented another node, which isn't.
Yes, sorry. I was using that as an example to say it isn't simply the issue with, if we get rid of this, the issue with A not being connected isn't that I left A all on its own, it's that I didn't connect the whole thing up. So if we have A, E, B, D, C,
Yeah.
if I create a tree here, that is a tree.
Yeah.
Yeah?
Yeah.
Now, at the moment, that would be considered a tree because this would be considered a tree,
Yeah.
right? It depends on the consideration because you can look at a subgraph and say, well, that's a tree.
Right, but you
Yeah.
can't look at the whole
So-
thing as a whole.
Yeah,
As a
that's
tree.
not a tree
Yes.
because a tree is a connected graph with no cycles, and at the moment there are element nodes A and E which aren't connected to the other bits.
Yeah.
Similarly, this is not a tree.
Because not all of them are connected.
No, but that's a tree
Yes.
and that's a tree.
Yes.
Yeah.
Okay.
So
fine.
a spanning tree is a tree, but it must include all the original vertices.
Right.
So it can't be a subgraph, basically.
So it must be.
Yep.
that.
Yeah. Has to include all. It can't be a subgraph. It must include all the original vertices from the original graph.
Okay.
Okay. A minimum spanning tree
Yeah.
is a spanning tree with minimum total weight. The weight being the lengths of the edges, essentially. So it still has to be a spanning tree. Spanning means it includes all the nodes of the original tree. Tree meaning it's a connected graph with no cycles. Connected meaning there's a path between every two things. Path meaning there's a finite sequence of edges such that blah blah blah. So it's a kind of Russian doll of definitions here going on. But yeah, so that's definitions. And what we're going to do in the next couple of videos, Kruskals and Prims, are algorithms for finding a minimum spanning tree.
Okay.
Okay.